Welcome all of you to river engineering course, in the last class we have derived Saint-Bennett equations. Today I will derive the next versions of the Saint-Bennett equations in terms of discharge, and also we will talk about how we can solve these Saint-Bennett equations. It is quite interesting lectures today and focusing on Saint-Bennett equations and its solver. If you look at this book, we have applied hydrology, V.T. Chow and D.R. Menment and May's book, which we are following for the Saint-Bennett equations derivations in terms of discharge Q and the flow depth, and also we have other books what we have been following it as a part of the river engineering course. Now let me look at going back to the contents what we are talking about. That we will talk about flow and geometry of the open channel flow or the rivers, how things are the difference. Then we will talk about how we can consider this contractions expansion zone and how we can write a new momentum outflow or the new momentum equations for the control volumes, rewrite again Saint-Bennett equations, and more detail we will discuss in it how we can do a classifications for distributed flow routing models. Then we have a solvent examples and we will show demonstrations of Hecker's river models, which is the solver of Saint-Bennett equations and the continuity equations. Let me go for very basic diagrams. If you look at a river, it looks like this. You will have a phthalate lines, the deepest, the depth, where the deepest depth will be there. That is what we call the phthalate line. The regions where having the perimeter is wetted, that is what the wetted perimeters, or symbolically we represent the P, and you have the flow depth, and this is what is showing the top width or the B of the channels. If you look at that, whenever you have a rivers, its flow varies it. So you may have the low flow here, this is low flow. You can have the flow at the top width, which you will be indicates is the bank full discharge, and sometimes you can have the flow in this level, which includes the river and the flood plain. Maybe this is the 10-year return period flood. So we have the flow variabilities because of the flow varies from low flow bank full discharge to the 10 years return period discharge when you have the river as well as the floodplain. So there will be the left bank, there will be the right bank, and when you go for the flood situations, if you look at that, there will be different roughness will come it because of the floodplains. There is a floodplains, there will be give a different flow resistance as compared to the main rivers, which is generally have a bed materials like a gravel, sand, but when you come to the floodplain regions, you can have a trees, bushes. Floodplain area can have a different land use land covers. So if you look at that, as the flow varies from the bank full discharge to the 10-year return period flood, when you comes it also occupies the space in the floodplain as well as in the rivers. And as you go for the low flow, the channel is confined within this flow. So the flow variations are there from low flow to the 10-year return periods flood or 100-year return period flood. So you can imagine it that the flow depth is a variability is there. The basic parameters of these in a channels like flow resistance, flow depth, the discharge, the velocity varies with time as well as the space. So that is indicating it the velocities varies with the space and the time. Here I can say that area average velocities and the flow depth can vary with a space and time. But most of the cases we simplified it to the one dimensional flow. One dimensional flow. So, we simplified it to one dimensional flow. That is what we have done for the Saint-Venant equations. Please remember that when you have the river flow, not only the flood plain and the river also interaction. There is a interactions between the groundwaters and the surface water. There is interactions between surface water and the groundwaters. There will be interactions, the water from the river to the groundwaters or groundwater to the river. They say there is interactions of the lateral flow from the groundwater to the surface water or the surface water. So, there are the mechanisms are working it with a different flow, different discharge, different flow resistance. Mostly we are looking in terms of mass conservation equations, momentum conservation equations. Similar way we can look for the also energy conservation equations. So, we have three basic principal equations what we can derive it, but those are all I can say is approximations when you look for real conditions like these figures is indicating for. So, the real conditions are much more complex. We simplified it and we try to write in terms of mass conservation, momentum conservation or the energy conservation equations. So, still we have the assumptions, still we have a lot of simplifications in term if you look at the complexity of a river systems. Now, if you look at the next figures, which is very interesting figures, it shows that the river is not a straight channels. Okay, we are not having the canals that is a straight channels with a constant slope will be there. Slope variability will be there, bed material variability will be there. There are the regions can have the island formations like this. Because of that, if you look at the velocity distributions, it changes it. Look at this, these are all the major velocity distribution. That's all this velocity distribution channel. And here the river has the curvatures, the meanders. The river has a curvatures. But in this case, because of the river expanding and contracting it. There is expansions and the contractions out of the river is happening it. There are the river bend formations are there. There are the island, the bar formations are there. So, if you look at this, river is not a simple channels like canal where you have a constant slope and main bend channels. It has the natural channels. Because of there is expansion, contractions, river curvatures or the river meandering formations will be there. That is the reasons if you look at this major velocity distributions which indicates in the very complex process what is happening it in terms if you just look at the velocity distribution. If you look at these figures which are very interesting figure for us and we look at to simplify the river flow problems. Like if you look at that I have just a stone hit here and we have a very gentle bed slope S naught, okay, very gentle bed slopes and assuming it that there are some bed perturbations or bed materials like the stone formations are here. What is going to happen it? There will be part where the flow will be uniform flow. That means the flow value like velocity and the depth. The variations of the velocity and the depth with respect to the x, that means this is if I define the x is a longitudinal directions, that remains very close to the 0. In that case we can consider the uniform. In other way around, the flow depth and the average velocity doesn't change with the space or doesn't change with x coordinate directions. If it's that, then we call uniform flow. And this is a very simplified case when you have the uniform flow. But there are the cases because of the stone formations, you will have the effect. That what will be the gradually and rapidly under the varied flow conditions, we will have a gradually variations. That means del H by del X, these variations is there but this quantity is very small. You can see that slope of water levels variations is there, but variations is not that large, it's very small. If it is that the conditions, we call gradually varied flow. But if you del H by del X varies considerably high, then we call rapidly varied flow. So these are the reasons we are just here, there could be a formations of hydraulic jump. There could be a formations of hydraulic jump, and there could be formations of your eddies formations will be there. So if you look at this way, if you just conceptualize with a simple channels, if you put some obstructions, you can see there are different type of flows are happening it, or flow reaches we can approximate it for analysis point of view as uniform flow, gradually varied flow, or rapidly varied flow. After the rapidly varied flow, there would be a gradually varied flow, like the free surface change will be there, but the change is not be significant. As the free surfaces flow depth is changing it, the similar way the velocity also changes it, as you know from basic mass conservation equations. So if you look at that way, there is a uniform flow, gradually varied flow, rapidly varied flow. As water resource specialist or looking at river engineering specialist, we need to look at what type of flow approximations we can do it when you try to solve a real life problems. Otherwise, it is need not to solve very complex equations for uniform flow or gradually varied flow. So we need to try to understand the river flow at the reach scales, also at the larger scales, like beyond the reach scales, what is happening it. That's what we try to understand it with these longitudinal velocity variations, as well as if you look at this, the flow classifications in the open channel flow. That's what also. Now we will come back to the basic concept what we have derived in Saint-Bennett equations in terms of three force components. Okay, one is the gravity force, another is the friction force. These two force is more, and that what is equal to mass into accelerations. That's what we have done it. But as we discussed earlier, river is not a constant width channels. There will be expansion and the contractions. If is that, let me I sketch the simple control volume for you. So if I look it, so I will have the expansion of the flow, which having the flow is the q amount of the flow is coming it at the delta x distance. Using the Taylor series concept, I can make it the q variability like this. So this is my control volume, and I can consider the small q will be the lateral flow per unit length. Small q will be lateral flow per unit length. That's what is the flow is coming it in this direction. This is my control volumes, and the distance is the dx. If this is the c, then if you have a q is amount of flow, volumetric flow is coming into the control volume, we can approximate using the Taylor series the flow variability at this surface will be this way. The same way I can write about rho beta bq is a momentum flux. So beta is considering the velocity distribution, momentum corrections factors. So rho bq will be the momentum flux, and that way I can also write it. If I rho if it comes out be v bq plus the variation of v rho bq dx. So more detailed derivations you can look at applied hydrology books. So that means you can have the control volumes, you can write the mass flux in terms of q and the momentum flux in terms of rho beta vq. That's what you can consider it. If it's that there as it's expanding expansions are happening it. Because of these expansions, if you look at that streamline, it will be expanded. These are the streamlines. These are the streamlines will be expanded, and there are the formations of eddies. There will be the formations of eddies. There are formations of eddies, formations will be there. Because of the eddies formations, there will be energy losses. Okay, there will be formations of eddies, and that's what will be conducting energy losses. That. So we are not going into 6 of the how the eddies formations happening it, how quantifying of energy. We are just quantifying energy as we are following this hypothesis of pipe flow. In a pipe flow, if you look at these eddy formations and all in a pipe expansion joint, we consider as a minor losses, and we try to establish the energy losses in terms of velocity head. The exactly same way for these expansions of channel expansions, we are following this pipe flow minor losses concept. We are considering the energy losses is related to the change of velocity head. That's what we are looking at. Okay, is a proportional to the velocity head through the length of the course, what is causing it. That means what we are talking about, that we are considering as equivalent hypothesis, that as the river expanding it as equivalent to a pipe expansion, as equivalent to a pipe expansions, you will have a formations of eddies. And these eddies, if you know it in a pipe flow, it has related to the energy losses related to the eddies in the pipe flow to the velocity head. The same concept we are using it here to quantify the energy losses due to the formations of eddies as the river expands, as the width is increases, that what will be related to the velocity head. And if that is considered as the eddy energy loss slope, AC stand for as energy loss slope, this is as equivalent to a frictional slope. So as equivalent concept, if you consider it, the force because of this eddy generated the energy losses on these contour volumes can define it as similar to the friction's slope concept. That's you just try to understand it. Because of this energy losses, what will be the additional stresses which is going to act on the surface, on the bed as well as the surface. That as equivalent, if you consider it as we have done for the friction slopes, the same way we can consider it, and we can compute it what will be the drag force because of the eddies formations, because of river expansions. And AC is a gradient of this. That's the reason we have a partial derivative of the velocity head, and is a proportional constant. Ke is a proportional constant, which is from experiment we can get it what will be the Ke value. So whenever you set up a river models, it asks it what will be the expansion contractions coefficients. That's depending upon your rivers, your physical model informations, you can include it what will be the Ke value for a particular river systems. So that way, if you look at, there will be a non-dimensional expansion and contractions coefficients. It's a negative for the channel expansion, positive for the contractions of the channel. So the basically the eddy energy losses because of expansion of the river are the contractions. That what we consider with these two equations as a energy eddy loss slope and the drag force due to the eddy losses. Now if you look at the next one, what I am to just revisit you, that when you consider is that the same contour volumes, okay, same contour volumes, I have the Q amount of the flow is coming it, and there are the lateral flow, small q amount of the flow is coming. Okay. and this is the x directions. So definitely this is making the velocity components. This lateral flow also is not the along these q directions. There could be a Bx, the velocity component along these x directions. This is the lateral flow and all the things. So now if you consider this is the control volume, where is we have the lateral flow what is coming it, and this is the control volume in and the out, then we can write it mass in flux like this. Okay, this is very simple way. You can find out this is a q and the smaller q into delta s. This is the lateral flow per unit length. So my mass in flux we can write it, and we can corresponding momentum will be the rho v q. Okay, mass into beta is the correction factors, momentum correction factors, and to the velocity is a momentum flux. Here we have used the momentum flux components because of the q discharge which is coming it's making a Vx component along the x directions. So here we are considering this Vx, the lateral, the velocity x components inside into this part into q into dx. So this is the momentum flux due to the lateral flow which is not coming along the q direction. It has the inclinations. Because of that, let us consider the Vx amount of momentum flux velocity is coming it as equivalent the momentum flux we can get it. So you know it, and we can find out what will be the momentum flux going out from this control volume. That's what will be the rho vq and its gradient. That's what is the Taylor series. If I try to look at net momentum crosses across the control volumes, just looking at influx and the outflows, we are considering the sign conventions of positive and negative. For outflux is a positive and influx is negative. Why it is that? Please follow Reynolds transport theorems which has discussed any fluid mechanics lectures. Also I have some lectures on fluid mechanics, so please go through it. Why do we have a positive and negative signs for the momentum fluxes? So net momentum fluxes will come out to this. So now if you look at that momentum flux, what we can earlier we derive it, now that will be the different part. So more detailed derivations and all you just look it in applied hydrology book. I am just skipping that part, more details, but if you write the momentum equations, Saint-Venant equations, you will finally find out like this form. So if you look at that, the additional components we are getting it because of this is expansion contractions point of view, this is because of lateral flow, this is because additional part we call it wind shear factors. So many of the times also when you have a heavy wind, big reservoirs are there, we can consider the wind force also acting on that. That part please do the self readings which is there in applied hydrology book. So the basically what I am trying to do is that we have derived the Saint-Venant equations in terms of now in terms of Q and the H and the A. So we have derived this the equations now the Saint-Venant equations in terms of Q, A and H variables, and we have include the SE is the expansion contractions energy loss gradient. We have considered the momentum flux because of lateral flow. We also consider the force part or the energy what is acting if there will be the wind force acting under the over the rivers, or mostly this is a significant when you have a big reservoirs. So there will be a certain quantity during the high wind speeds that will be also give a force acting on that. So we can include these wind shear factors here to estimate that. See if you look at this, again we are getting the Saint-Venant equations in terms of Q, H and A, and in terms of partial derivative of x and the t, but still it is a non-linear partial differential equations. Still we have that forms. Now we are going to we are going to discuss that how we can simplify these equations. Now as I discuss with you that if you look at the Saint-Bennett equations is a nonlinear partial differential equations, but not to solving this nonlinear partial differential equation is not that difficult, but most of the times is difficult to give appropriate river geometry. As I said it in very fast that river is quite dynamics, low flow, bank fold discharge, 10-year return period flow systems or 100-year flow return period systems all differs. That is the reason we need to give a lot of input data into a river models even if you solve these Saint-Bennett equations. That is the reasons and most of the times any of the all elsewhere in the world also getting a so detailed data along the rivers, the river depth, the land use land covers, more details it is not possible. So we try to do a simplifications, we try to look the dominancy behaviors, whether we need to compute as a Saint-Bennett equations or we need to do some simplifications on that. That is what we have to do it under this classifications of distributed flow routines. So if you look at the Saint-Bennett equations, it has a different terms, like there are the local acceleration term, convective acceleration term, pressure force terms, gravity force terms, friction force terms, and others what we have include is expansion contractions terms, the wind force terms and the momentum because of the lateral flow. So if you look it that way, the which are the significant order? Are they all these terms are the same magnitudes or the some are not significant? Like maybe some cases the local accelerations may not be significant, the more or less the flow is steady, the discharge variability is not there. So we can drop this local acceleration term. Similar way, can we drop this convected acceleration term? In which case we can do it? Can you drop this expansion contraction point? This is depending on the rivers. If either expansion contractions is not there, you can drop that part. So the basic idea is to look at the dominancy behaviors, because each terms we have to try to know it what is the order of magnitudes. Is it a significant? If it is not significant, we can neglect that part. That is the approach we will follow it. This equation has to simplify it into one dimensional distributed routing, as I said that, but many of the causes we have to try to understand it, what it actually happens it. Like this example what I said it earlier, if you have the flow, there are the flow can change from critical, the subcritical or the supercritical. More detail about the critical flow we will discuss later on, but you try to understand, as you know from basic hydraulics, that subcritical and supercriticals. Then in subcritical the flow Froude number is lesser than 1. So in that the conditions what it happens is that if you do any disturbance, it propagates in both upstream and the downstream. That is what it happens it, that is what is called backwater effect. So that will be the backwater effect. In case of the subcritical flow, we will have a backwater effects. Basically when you look at the Saint-Bennett equations, the classifications means we try to look at all these terms in Saint-Bennett equations like local accelerations, the convective acceleration, the pressure force terms, the gravity force and friction force terms, which are the dominated component, which are the significant. Like for example, in case of the steady flow, the local accelerations terms will not be that significant. So we can drop that part, we can consider other 4 terms. The basic idea comes here to know it, that how we will be dropping or we will be approximating the sum of the terms in the Saint-Bennett equation, so that we can easily solve it with a limited river geometry data set. That is the basic idea. When you have a very limited river geometric data, you can do a order analysis of each terms and find out which are the terms are the significant and which are the terms are not significant. Based on that, you can drop the terms. For example, if you have the subcritical flow, as you can understand from basic hydraulics books, that the subcritical flow matters for us to know it. Whenever you do a disturbance, it affects both upstream and downstreams, and that is the cases you can have this local accelerations component and convert it and pressure terms. For these conditions, the lumped routing methods will not suitable when you have the subcritical flow, when you have a backwater effects. Now, if you look at basically what we try to do it when you talk about these Saint-Bennett equation solutions, when you go for the hilly area, the flood plain area, the slopes considerably changes, the gravity force components is considerably changes. So, we should try to look at the force dominancy part. Many of the times we neglected the local accelerations, the convective accelerations and the pressure terms. Then we have a kinematic wave models, where is very simple model, the bed slope is equal to the friction slope. It is very simplified now. If you are considering that local accelerations, convective accelerations and the pressure terms are not that significant. So, that means you have only two terms, the friction slopes and the bed slope. That is what will be comes out to be the Saint-Bennett equations approximation. That is the approximation. When do it, we talk about kinematic wave models. That means S naught is equal to SF. It is very simple models, and we can solve the cases very easily. Even if in Microsoft Excel level, we can develop a model, river models, when you have a kinematic wave models, S naught is equal to SF. But there are the cases we can neglect only the local and convective accelerations, not the pressure terms. You can consider the neglecting this only this local and convective accelerations, then we call diffusions wave models, and if you consider all the terms, then we call the dynamic wave models. So, we have now the classify the three different approximations. The first approximations we consider it the local acceleration, the convective acceleration terms and the pressure, they are not that significant order. So, if that is the conditions like hilly area where the slope is much larger, so you can approximate the kinematic wave models to do the river routings. But when you come back to the regions where there is a the pressure variations are there, water depth variations are there, but local acceleration and convective accelerations are not that significant, then you can use diffusion wave models. If you consider as it Saint-Bennett equations, then we call the dynamic wave models. So, whenever you do the flow routings using the Saint-Bennett equations, we can look at the other, whether you are doing it kinematic wave models, diffusions wave models or the dynamic wave model. Now, in equations form, if you look at that again, coming back to this, we defined in two terms, is a conservative and non-conservative. If you look at this first continuity equations, and which have conservative form, because we in terms of mass flux we do it. So, that is the reason say you don't have any approximations when you do the conservative form of equations, but in non-conservative form you write in terms of velocity and the flow depth. There is not exactly in a mass form, there is approximations that the discharge is equal to area into the velocity, that approximations which gives a non-conservative form. That is the reasons we put it a non-conservative form, because maybe some cases these conservations of mass may not hold good. So, that is the reasons we call it non-conservative forms, as we have a conservative equations and non-conservative equations like this. The same equations, only we have put it here, and there is no lateral flow. Okay. Same way, if you look at that, you can have a conservative forms which will be in terms of q, and non-conservative form in terms of the v. Okay, if you look at the velocity and the flow depth, and there are certain assumptions, like if you are considering these two parts, again just time to summarize that, you will have a kinematic wave approximations. If you consider these three components, then we call diffusion wave models. If I consider all these components, then you will have a dynamic waves. So if you look at this, these are the equations in Q and A, the Q, V in and Y is the flow depth. All this only two equations we can use it to solve these equations, two equations for the two-way dependent variables like the discharge and the area, or the velocity and depth. If you solve it, you can do it, but as I said it, it is not possible to solve these equations mathematically. It is getting the flow geometry data and channel geometry data and the flow resistance, all are not easy to for a natural rivers. So that's the reason we do certain degree of approximations like kinematic wave models, diffusion wave model, or the dynamic wave model. Now let us come to have the solutions to example problems. In a river, the average velocity and the water depth are measured at the three sections. Okay, is a velocity is given v1 h1, v2 h2, v3 h3, and that's the velocities flow depths were measured at 1 hour intervals. Okay, justify the applicability of the diffusion wave approximations for these reaches. So looking these velocity and depth measurements, we can justify it whether the applicability of diffusion wave approximation is okay for us. So basically we try to look at all the terms of these Saint-Bennett equations and try to look at whether in this case diffusions wave models, if you consider it, is it okay for or not, considering the velocity and the flow depth data. This is the measured flow depth and data. So if you look at the velocity data and the flow depth data, so if you look at these variations and you look at this, so there is a velocity. So if you look at these equations, we try to look at the gradient of h in terms along the x direction, gradient of u in the x directions, and the gradient of u in the t directions. So we try to look at the velocity, the temporal gradient of the velocity, the spatial gradient of velocity, and the del h by del s. Then we try to look for each terms, how the significant order of each terms. If there is not significant order, then you can approximate it as a diffusion wave approximations. Now if you look at what we have done it for a real river cases, we try to find out the gradient. Okay, del u by del x is a gradient. That's what we follow the central differencing scheme. If I follow it, we know the u3 u2 by do delta x, here is a 2 meters, I can compute it what will be the gradient. Same way at the time t, I can know the gradient. So I can compute what will be the average del u by del x at the central difference scheme, I can compute that part. Same way we can find out what is the temporal gradient of the VU values. That's what we can put it, and we remember we can put it in terms of minutes, 60 minutes, and you can get these values. Now if I look at del u by del t and I look at delta h by delta x values, and that's what I can compute for the t equal to 0 as well as t equal to same way we having the central differencing scheme to find out the gradient h with respect to the x, that can be approximated as delta u here as well as is a simple central differencing methods to approximate what will be the gradient. We have got the gradient like 1 by 20. So if you look at this way, now for each point we just substitute the value. We just substitute this value. Okay. So each part we just substitute value in terms of the bed slope and all these terms. If I try to look at that, you can easily find out this x4 is much lesser. The x4 part is much lesser than x1, and x4 is so if you look at these two terms, okay, these two terms are much lesser than these two terms. So we can always tell it this is not significant as compared to x1, x2. As compared to this x1, x2, these terms are not that significant. If I consider that part, then I can assume it, because this term is very less, the x4 terms are the very less, we can easily term that we can use diffusion wave approximations for this case. So this is the examples are indicating that you can have a velocity, you can measure the depth, and from that we can find out what type of models we can use for Sand-Bennett equations. You need not to know is total dynamic wave models to use it, whether you have to diffusion wave models or you can use the kinematic wave models. That the examples is given it here. And if you look at the next ones with examples where we are talking about a series of the velocity and flow depth are measured along a river, and the flow field measure data shows the relationship with the flow depth, velocity along longitudinal directions and the time as this. Okay. And as given below, the bed slope also have a variability along the longitudinal directions. Estimate the friction slope of the river at the time equal to 1 hour, x equal to 100 meters. Okay. These are very theoretical questions, but if you have that velocity variations as a functions of x and t, and you have the flow variations in x and t, and bed slope is variation x and t, then we need to compute the friction slope. So here we have to use the Sand-Bennett equations, because the functions are given, we need to compute the partial derivative of velocity and h in space and the time domain, in this case only x domains and the time domain. Once you know it, substituting this value, we can solve this problem. So we compute this partial derivative of u at respect to the x time, and we have the x naught values. So you just compute the partial derivative of u, partial derivative u with respect to t, h with respect to x. You know all these functions, substitute these values like this cases, substitute these values, and as you substituting these values into the SF, all these equations, and finally you substitute the time, you will get the SF value. So this is the examples where you may have 1,000 data, and if you can develop the relationship functions between the flow depth, velocity and the bed slope, you can find out what could be the friction slope factors. That's the demonstrations we have given it. Before concluding these lectures, I want to just show the few minutes on these models. What we have set up is called the Hecker's river models, which is the more or less the Sand-Bennett equation solvers, and that's what we have set up for these river stretch. If you look at these, all are the cross sections number. So if you look at it, very detailed cross sections are there, and we got this all this river cross section. There are the barrages, there is the river photographs. So if you look at very detailed cross sections, data are there, and each cross sections we have a showing it the flow geometry, the cross sections like the depth, the flood plane, the width, the geometry, all we have set up about the Hecker's models, and there are the river intervention structures like these barrages are there, and the channels part is there. So if you set up in a Hecker's models, which is a nothing else is a Sand-Bennett equation solvers, if you set up these models and see these some field photographs, this is the field photograph the wear systems. If you look at that in a model setup, it looks like this with having these structures, and you have this bridge pier, that is what you can see it, and you have abutment. All this can show like this. This is the model framework, these are real conditions, and this is the model simulations, the flow depth. This is what we have done with a ADCP survey to show these velocity variations. Okay, if you look at this main channel and velocity variations, and this is the what, because in models, is a one dimensional models, we get a area average velocity and area the flow depth. So that's the reason. So in the models we get it average velocity, but in case of ADCP survey we get a very detailed velocity distributions. From that we try to find out what will be the average velocity. Here if you look at it in some reaches, it can velocity go as high as 1.5 meter per second, and some cases it can be as low as 0.3 meter per second. So some cases it will be 1.5 meter per second, but HACRS gives a average velocity conditions. That is what you try to understand. This is the field data, this is the average velocity condition, and this is the field photograph, how it looks it, but in a modeling framework how it looks it. Okay. So more details about HACRS and all will phase wise we will talk with more details with our case studies, but you try to know it as a HACRS, as a Sandvinette solvers. We can set up the models and we can have a case studies like this. Also we can look at that. This is the real conditions where you have the breaching of the wear, or the old wear is a breaching part. The same things are there in HACRS model setups, how we have put it and how this velocity we have measured it and how the velocity is simulated that. So that's there is one is a field conditions, another is HACRS modeling setups. Those the variations you try to reflect it, how it does it look it in field conditions. When you observe, this is the field level photographs and the velocity measurement, and this is the one dimensional HACRS models output is shows that how the things are the different when you do the modeling of Sandvinette equations. We are going confidence on that. So before leaving it, that's just time to put it like this. If I look at this river length is considerably around more than 70 kilometers. So if you look at that in the river, there will be the longitudinal profiles like that. There are the deeper zones and the smaller zones, and if you have a 60 cubic of discharge, the depth variations will be there. 560 cubic discharge, you will have depth variations like that. So the model can simulate it more detail of the longitudinal profile, how the velocity varies it, how the flow depth varies it, as we have a 60 cubic or 560 cubic discharge. If there will be a barrage in case of the 60 and 560 cubic, how there are the two barrages are there, how the flows are happening it. So if you look at that, you just look at these figures, the HACRS models, how it's help us to know it. If I have a multiple reservoir structures, how the depth is increasing and where is the depth is more and less, that all details we can understand it in a mathematical frameworks when you set up HACRS models like what we have done it. For this is the present case without the wear structures. These are two the cases with the wear structures, how much flow depth availability will be there, how much the velocity variations are there, all we can compute it in a HACRS models. With this, let me conclude this lecture. Thank you.